So I'm going to use those 5 minutes to just dance. All right, so welcome everyone. Thank you for being here on this last day. I'm usually one of the people who's not here, so it's nice to see what the room looks like. So I'd like to talk about something which is actually we've been working on for about a year now, and has been quite interesting from a statistical perspective. I'd like to work on not completely standard setups, and I think this one brings fairly interesting characteristics. And basically my hope during this talk is to convince you that it is indeed quite interesting and that it's definitely worth a look. So we have a couple of papers that are in Colt and ICML respectively, but you can get them on the archive. So this is joint work with Victor-Emmanuel Brunel, whose name is too long to write, Ankur Moitra, and John Urschel, who has the characteristic of being a professional football player until September, and then of course he met DPPs and decided to let go of millions of dollars to do that full time. All right, so let's start with talking about what this talk is not about. And it's a little of a weird place to start, but this is something that probably most of you are familiar with. And this is an example from Alex Lafermont's work with El-Gawi and Banerjee on fitting some binary graphical models to this US Senate data set. So the data they're getting is whether senators voted yes or no to a particular bill, and they observed these long vectors of plus and minus one. Let's say plus one for yes and minus one for no. And they wanted to reconstruct some sort of a covariance structure. So here it's really the Markov random field associated to it. And the goal was really to learn the graph. So at the end of this kind of paper, what you see is a picture that looks like this, and so it's very nice. I recovered the fact that Democrats tend to vote the same way and Republicans tend to vote the same way. And usually the final output is this graph, and maybe you're going to do some visual clustering on it or something like this. All right, so I argue that when if you've been at enough of those talks, this is not the only story that you're getting, that this is not the final output. There will be some other output. So the model that we're looking at, just to see a little bit what's under the hood, is typically, so for binary data, we have what's called an Ising model. Here I write its probability mass function on the space of vectors of plus minus 1 to the n. Here I use capital N, and without external field. And here the parameter you're interested in estimating, the parameter of interest, is this matrix, this n by n matrix, capital J, that's up there. All right, so here's my capital J, and what I want to do is to estimate it, and for that we typically make some sparsity assumption on what capital J is, and what you saw, those green lines that were before, correspond to the sparsity pattern of J. So what's nice about this model is that, if I were to describe a full distribution on all binary vectors of length n, I would have to specify an exponential number of parameters 2 to the n, but this one actually reduces it to only n squared by making the assumption that only pairwise interactions actually count. So this is quite interesting if capital N is much larger than n, as is often the case, or certainly 2 to the n is much larger than n. So this is nice, and we can do things, and there's a long line of work on this that mostly worked under sparsity assumption, or some we've worked on with Quentin on some other structural assumption. But at the end of the day, a lot of it can be solved using the ideas from logistic regression. Okay, so it was an idea that was introduced in this paper by Ravikumar, Wainwright, and Lafferty, and a lot of it can be solved using fairly standard statistical methods. So it's interesting, and it's not trivial. There's lots of complicated correlations going on, but at the end of the day, when it comes to statistical methodology, it's not too novel. However, one thing that's actually an issue is that it's still very hard to perform conditional distributions of some nodes given others, or to compute the marginal distributions of a subset of nodes for this kind of problems. And this is not a problem if you're interested in outputting a graph, but it starts to be an issue if you start looking at the second promise of those models. All right, so some of the talks that you will see will tell you, well, maybe the nodes of this graph corresponds to symptoms, and some of them corresponds to disease. And what I'm interested in is to understand, for example, in this case, what is the probability that a patient has leukemia, given that she has high blood pressure, high heart rate, fatigue, and no temperature. All right, and then I don't know the rest. So computing this conditional distribution is actually computationally hard, and corresponds. I mean, it makes use sum over very large spaces, and we don't really know how to do that for large systems. And it's led people to consider other models. All right. So another one that's slightly maybe a bit more vain for you, Richard, is to understand the some recommendation systems. So those models are also quite interesting. So you have a bunch of objects that you can buy. So here, probably it's a specialized IT website, and they want to know, what to recommend to their customers, and particularly want to know, given what they have in their basket, what is the next most likely thing they would want to buy. So here, for example, let's say that we know that a particular customer has bought this Samsung phone and has not bought this MacBook, but the rest we don't know, and now we're interested in understanding what is the probability that this person is going to buy the iPhone X. All right, like up there. And here we would want to say, well, if you already have a Samsung, maybe you don't want to buy an iPhone X. And so we need to find a model that captures that, and the Ising model will do that with negative associations, right? And so the problem is that it's not going to be very useful for us to compute those conditional distributions or marginal distributions. So in this last example, one particular phenomenon that arose is usually referred to as diversity, and in this example, it can be particularly important. Arguably, it's not that important for the medical example that I gave. And in the example that I gave, you could argue also that the data that you get displays diversity on its own, right? People do not buy 15 different phones in a particular basket. They buy things that tend to be separate from each other, and so potentially you could learn what diversity means from those baskets. And what we would like to do also is to find a model that features diversity, and a model that could actually allow you to do this marginalization and conditioning efficiently, certainly more efficiently than what the Ising model allows you to do. And so but we don't want to let go of too many nice properties of the Ising model. In particular, I don't want to have more than n squared parameters. All right, n squared was a pretty decent number for me. It's sort of an idea that if you're trying to understand interactions, this is the minimum number of parameters you're going to have. So let's see what we can do with this. So the answer to that, and this certainly did not come from me, is one answer to that is using determinantal point processes. All right, so determinantal point processes, and for the rest of the talk, I will just say DPPs, are point processes, and they can be either discrete or continuous. It's nicer to show pictures of continuous point processes, but it's going to be more relevant for me to talk about discrete determinantal point processes. So they were introduced in physics. I think they were officially pegged by M.I.T, or I don't know how to say this, to model fermions, which have a natural repulsive nature. So that's why they're interesting for diversity. But you can trace them back to old probability work, back to Dyson, I believe. And they actually show up in the study of eigenvalues for random matrices or integrable systems, because those things tend actually to repulse each other. There's actually a nice paper by Borodin that you can read. Usually the problem is once they get to a determinable point process, this is the end of the road. They're happy they can compute everything they want. So those things are actually tractable. And that's one of the nice things, and that's what's going to bring us marginalization and conditioning easily. And now, more recently, there was this book in the series Foundations and Trends by Alex Kulesa and Ben Taskar, and they started showing how you could use these ideas in machine learning. All right, and that's the first time I saw these things. And to be honest, what really caught my eye was that they were really beautiful mathematical objects, more so than how to recommend an iPhone X, to be fair. And so let's see how we can work with those. Okay, and so for those, Andreas Krause actually in his talk mentioned the fact that he was really interested in computational aspects, and this is part of a subset of distributions for which those computations that we're interested in are easy, and you can do sampling, you can do a bunch of things. So there's after this Kulesa-Taskar book, there was a whole bunch of applications where you could use this. The one that was featured in Andreas's talk, and I'm going to mention only a couple of them, so is image segmentation, right? We wanted to extract the cow from the background. There's what is another one? I don't know. You can use it for Well, okay, let me, so spatial statistics is actually a big one. They use it in forestry, for example. So those are for continuous point processes where you want to model the fact that trees tend to grow up away from each other. And there's a nice survey on applications of DPPs that just came out in exam this year. Okay, so, you know, I hope I've convinced you that they were important, but now let's see what those things are. So I'm going to start with the general definition. So here I'm going to have a general state space, and for the purpose of those couple slides, you can think of the state space as being R2. So I'm going to draw a set of points in R2 on the plane. And the way I'm going to characterize this, the distribution of this point process is by using a so-called correlation functions. You might call it a joint intensity. And it's essentially computing the expected number of product of numbers of points that you get in a collection of disjoint subsets of R2. All right, so I give you A1 to N, that are disjoint subsets. I count how many points I see in each of those subsets. And then this expected number is given by the expectation on this product of those sets of this so-called correlation function. All right, and if I give you this, I actually fully characterize what the distribution of my point process is. If I give you rho from x to the n to r, so here from r to the n to r, I give you the distribution of my point process. And you know, this is a lot of point processes, and a DPP is a very specific one where rho has a very specific form. It's actually for each evaluation of this intensity function, you actually compute the determinant of a matrix. All right, so if I want to evaluate rho at points x1 to xn, what I do is that I form this matrix where the general term is k of xi xj for some k, and I'm going to put everything into a big n by n matrix, and I'm going to compute its determinant. All right, and if I do this, I'm going to actually get a valid correlation function, and I'm going to actually try to understand. So I've sort of transferred learning a rho from R2 to the n to R to, in particular in our case, to just parameterize everything by k from R2 squared to R. Okay? So I've put some structure by doing this, so it's a subset of all processes. Yeah?
Integral is a Cartesian product or a union?
It's a Cartesian product.
Why did the AI need to be disjoint?
Because that's the definition.
So K is positive definite, or?
It doesn't have to be, but well, that's what we're going to be considering. Okay? Everybody took a mental picture of this. We're actually going to simplify that quite a bit, but the main reason is because I wanted to show you what DPPs look like and what repulsion, what I mean by repulsion. So if you actually sample uniform points on, say here, the unit square. So here, DPPs tend to be infinite. All right, in R2, you have an infinite number of points, and what you're going to do here, you're going to restrict yourself to a particular small window. And if you do uniform, you're going to see clumps of points, right? That's the usual notion that people just don't. If you ask someone to do it, they're going to put those points far away from each other. And you know, there's this understanding that this typically does not represent uniformity. You would see clumps, and as you can see on the DPP, you don't have this. All right, points tend to be spread apart. And this is the reason why they're used in numerical integration. At some point I mentioned this because they're closer to, you know, well-behaved design, and they tend to enforce diversity if you handle this property the right way. Yeah?
What kernel did you use to make that one, and how do the clumping properties
Yeah, so the kernel that I used is a copy-paste from Kulesa and Taskar. And because so there's an hour package to do that, and typically people use a Gaussian kernel or something like this.
So if you change like the bandwidth of your Gaussian, does that change how much clumping you get, or what's sort of the intuition here?
So it will certainly change how many points you see in a particular unit of space. If you change the kernel, it's going to change things a little bit. There's going to be, right, so here, I don't know, maybe there's some direction along which things tend to be more spread out than others. If I had an isotropic, this one, I'm not actually sure on the top of my head what kernel was used for this, but I would guess Gaussian is a pretty good candidate for this. So, yeah. Okay? So we're going to move for the rest of the talk to discrete space. All right? R2 now becomes the set of integers from 1 to n. And that's the one that's relevant in machine learning. And here, so if you actually consider a set of disjoint A's and you write this thing, right? So here I replace my correlation function by the determinant of my kernel matrix. So if you actually do this, then you can see that if you pick a particular subset of points a union of sets, so here I'm going to take a partition of the set S, which is a subset of 1 to n, right? That's the set in which I live. So I take a partition, and you can see, because I have S of those guys, really what I'm doing is just taking S different numbers in 1 to n. And if I actually compute my matrix at those points, k of ij, I compute the determinant. I mean, either you see it immediately, or it's going to take you a minute and 30 seconds, I promise. You're going to be able to show that now you can actually compute probabilities of inclusion. So for any given set S, which is a subset of 1 to n, you're going to be able to compute the probability that S is included in the realization of your DPP. All right, so your DPP now gives you subsets of 1 to n, and you're going to be able to compute for each given set the probability that's included in your realization. And by inclusion-exclusion formulas, you're going to be able to actually find back exactly what the probability that y is equal to a given S is. But it's not as nice. This one is exactly given by a determinant of a matrix, and the matrix is, again, the matrix here, there's only one, so that's the matrix K1, 1, 2, K, and N. It's capital N by capital N. And what you're doing is computing the determinant of the submatrix of this matrix, whose rows and columns are indexed by capital S. Okay? So this is the determinantal point process on the space 1 to n, and again, it generates subsets of 1 to n, or equivalently, if you want to go back to this US Senate example, you can, of course, put a bijection between subsets of 1 to n to binary vectors of length capital N. So in a way, it's actually a distribution that has similar features to this Ising model we've seen before. Okay, so as I said, you can actually use your inclusion-exclusion formula to actually compute the probability that y is equal to S. It's not that ugly, but you have to take some absolute values and take k sub S complement, remove it from the identity. So we're not really going to work with this. It's much nicer to work with the determinant itself. And the notation I'm going to use is to say that y follows a DPP with kernel k. And of course, k will be my parameter of interest. And if you have a slightly statistically bent mind, which I hope everyone in this room does, you're starting to think, okay, how am I going to estimate k? So let's see just a quick example. So here I have this particular kernel, k, which is 1 over 20. So here I actually put this 1 over 20 because I wanted the eigenvalues of my kernel to be between 1 and, well, okay. I need my eigenvalues to be between 0 and 1, I'm sorry, because I actually want this determinant to be a probability. And so here, let's say if you want to compute the probability that 2,4 shows up in your outcome, you just take the second row and second column, and then you take the fourth row and fourth column, and that gives you the matrix that has 7, 1, 1, 9. You compute its determinant. Maybe you've forgotten, but the way you do it is by doing 7 times 9 minus 1 times 1. You divide by 20 squared because this is a matrix. Okay, anyway, so, and then you get 0.55. All right, so that's how you compute those things, and it's not very complicated, as you can see. So let's say we want to estimate k, and the first question you may ask, this is not a very traditional model, so identifiability is a real issue. And so we can ask the question, well, if I give you 2 DPPs, or if I give you a DPP with different kernels, does it imply that the kernels are the same, right? Is this an injective map? And it turns out that this is not true, so it's actually an old result from the early 80s that was not stated like that, but it was stated in the context of DPPs by Kulesa in his PhD thesis. And what he showed is that two kernels give the same DPP if and only if they're what's called similar. Actually, in the paper, we write D-similar, but that would make me say dissimilar, which is a little annoying. And so if they're similar, meaning that if you take k and you pre and post multiply it by a matrix with only plus and minus ones on the diagonals, so the same D, then you get a k prime, then those give actually rise to the same DPP. The right to left direction is pretty obvious, right? If I start taking the determinant of something on the right, I can take one of the diagonals, push it to the right, and then d squared is equal to the identity, and it's going away, right? So going from the right to the left is pretty obvious, and then you can go from the left to the right. It's a little bit more work, but you can actually do it. All right, so those are definitely not identified as something that we should probably keep in mind when we start doing maximum likelihood, which is actually the method that you see in most computational aspects. There's a lot of global maxima to your expected log likelihood. Right here, there's 2 to the n minus 1 of those guys. Okay, so this is my goal here. Now that I've introduced what DPPs are, I want to learn them. I want to estimate k. So I'm going to give an n, little n ID copies. So capital N will be reserved to the size of the state space and little n to my sample size. And they're going to have some unknown k star underlying those things. And I want to estimate k star, of course, up to similarity, because that's all I can hope to get. And what we're going to do is we're going to place ourselves in the setup, which is not the usual minimax setup. Forgive me, Sasha. It's already hard enough like that. So we're going to place everything away from 0. So we're not going to let our coefficients shrink to 0, and which is going to have a clear implication is that we're going to get 1 over n type rates. And of course, we're going to be 1 over square root of n type rates. And we're going to try to understand what's in the numerator, right? What is the geometric complexity of this space? So typically what we're going to assume is that either kij is equal to 0, so there's nothing there, but if there's something in the entry ij, we want this thing to be bounded away from 0 by some parameter alpha. Okay, and we're going to denote this class by script k sub alpha. And so here's the spoiler, is that this is the rate we can actually prove. So let's look a little bit at the measure of performance. So we're looking at entry-wise sup norm in those matrices. Now, of course, I need to quotient out this similarity equivalence class. So I'm saying if I take the best possible k hat that's aligned with k when I do the right similarity, I want this thing to be smaller than epsilon with high probability. And to do that, so I wrote this in the computer science type terms, but to do that, I need to have n which is larger than those things. All right, so let's forget about the logs for the sake of the discussion. We're going to have a rate which is actually quite standard. This is 1 over epsilon squared. This is essentially, if I told you that an entry is there, this is the price you would have to pay to estimate its magnitude. The 1 over alpha comes from some square root somewhere. We'll see it in a second. And so this is not very interesting. This is basically Hubner's inequality. What's interesting is this, all right? So here, there's going to be this quantity, script L, that we call here, as you can see, the cycle sparsity. So we'll see how this thing actually shows up. And that's essentially controlling really the bulk of the problem. All right, so we see that we have a 2 over alpha to the power L. So if alpha, think of alpha as being smaller, even if we went to some minimax setting, this alpha would tend to shrink in a worst case towards 0. This gives you an exponential blow up in L, so we want to understand what this L is. It turns out that this L is also optimal. So those rates are actually minimax optimal. And so we really need to understand what this L means. And we'll see that, and I think that's what's quite interesting about this work, is that this L comes from some, so we've seen some interplay between, convex optimization, even non-convex optimization yesterday in Andreas's talk, and we want to, there would be some, we've seen that a lot in the past 10 years maybe, but I think this features an interaction with combinatorial optimization, which is not something that I have seen a lot. And this cycle sparsity comes from combinatorial optimization. Yeah.
Just connecting back to some of the early applications, like with these SINET graphs. So K is going to give you some information about that adjacency matrix and how, and the corresponding conditional probabilities, I guess. So when you talk about learning up to these similarities, how do these similarities relate to those conditional likelihoods that you were ultimately interested in?
So whatever D I pick, I'm going to get exactly the same conditional distribution, right? It's the same distribution no matter what D I pick.
Yeah,
but
okay.
Let me actually be you and ask, I thought you were going to ask the question that's a little touchy, which is, well, you want to estimate, so let me ask it for you, is you want to estimate, you just told me you wanted to estimate conditional distributions, and you're estimating K in this entry-wise sup norm. Why is that the right norm to look at? And my answer is probably not the right norm to look at. This is a first thing to do. Okay, any other question? That was a very good question, thank you. All right, so we're going to do the method of moments to start. All right, hopefully I'm going to have time to get to the maximum likelihood estimator, but I think where it's really interesting is in the method of moments. And so actually, this problem, remember the first example I said is just to spit out the structure of the graph and to show you where the edges are. And if that's all you want to do, this is super easy. You get this from just computing first and second moments. It's extremely easy, right? So we know that the probability that J shows up in Y is the determinant of K. Well, here there should be a JJ, right? So this should be the determinant. This is the beauty of those things. Oops, no.
I think it's correct.
K sub J. Yeah, that's true. Actually, that's correct. Thank you. With the braces, it's correct. With the braces, it's correct. Thank you. So it's the determinant of the matrix where I extract only the jth row and jth column, which is just the jth diagonal element. So I can actually estimate all my diagonal elements by just looking at the proportion of realizations that contain the jth element. And then I can also look at the determinants of size 2 by 2. By looking at the proportions of realizations that actually get the pair JK, and that will give me this KJJ times KKK minus KJ squared, which is a 2 by 2 determinant. And of course, the first one is giving me readily an estimator for KJJ here, and the other one I have to use the square root because I just need to extract my KJK from this square element, and that's where I pick up the 1 over alpha term. Is because, well, it's not very well conditioned around 0, so that's why I need to keep it away from 0. And I'm sure if I were Sarah, I would actually know how to handle this thing around 0. All right, so, and I need to put a positive part. It doesn't matter, because for large n, it's going to be positive. So, and this is just a standard application of Hovding's inequality plus handling the square root, and you get your usual square root log n over n because you have a max. And if you invert this to write it in terms of computer science, you get you need n to be larger than log n over alpha squared epsilon squared to make this term less than epsilon. This is done. I could just call it a day, show you a structure for the US Senate, but it would not be that interesting, would it? And so what I want to do is to do more. I want to be able to compute my marginals or to compute my conditions. And for that, I actually need to understand what K is. And the determinant of the K when I put absolute values in each entry is actually different from the determinant when I start having plus and minus ones. And so the bulk of the work here is going to be about recovering what the signs of K are. And of course, we're not going to need to remove all possible uncertainty on the sign. We need to understand K up to D, up to similarity, right? And there's this plus and minus. So that's just flipping the signs of a row and a column simultaneously. OK. So how do I find the signs? Well, here I promise you we're going to go to combinatorial optimization. And you know that combinatorial optimization is mostly about graphs. So let's build a graph out of it. And that's the graph that we've seen before. That's just a graph that's induced by the sparsity pattern of K. I don't think I should say more about this. But if you want to hear more about how do I go from K? So here star means it's a non-zero. 0 means it's a 0, and just the sparsity pattern of K, I can view this as some adjacency matrix of a particular graph, and I can draw this graph. Okay? So now I'm going to look at two types of things in this graph. And the first type of element are path. Right? So if you look at the previous one, there's a long path. And what I claim is that paths actually do not carry any information about the signs. And the reason is because when you have a path, and you start doing all these similarity things, you actually get all possible sign patterns. All right, so here I wrote only 2. So there's a little bunch of dots. But essentially, right, so I start with this thing, and I can just put minus, minus. So here all my matrices are symmetric. And if I went all the way, so here I don't need that many, but if I went all the way, I could get all possible, well, 1, 2, 3 sign patterns that I can actually think of. Right, so basically, there's nothing to learn. Just so another way to put it is that if my graph was a complete path, then dissimilarity would mean that signs don't carry any information. You could put any sign pattern that you want on K, you would have exactly the same distribution. And it's going to be this true also of subpath of my graph. Okay, so I'm going to just try to forget about those paths and try to see, okay, so where do I get information if I don't get it from path? Well, I get it from closed paths, which are known as cycles. So let's look a little bit about what a cycle can tell me. And here you can see that, let's look at two examples. So here is K and K prime. Okay, so this K, the sparsity pattern of this K and this K prime are the same. They correspond to this 4 cycle. And if I start replacing the plus by a minus in the upper and lower upper right corner and lower left corner, you can see that those two matrices are certainly not similar to each other. There's no way I can get one to the other by pre and post multiplying by diagonal matrix. So that means that they will give me two different DPP distributions. And so that means that this cycle will carry information about the sign. So that's what I actually need to consider. And you can check very quickly that recovering K up to similarity is the same as recovering the product, the sign of the product, or the product of the signs, which is the same thing, of the entries of Kij along a particular cycle. Right? So every time I close a cycle, I'm going to have some constraint on what the product of the signs along this cycle should be. And that's exactly the same as recovering K up to similarity if I can do that for all possible cycles of my graph. Okay?
All cycles or all cycles of the given
All
length?
cycles. Well, right now, if you look at Engel and Schneider, all cycles. So, and I mean, you can see that actually from this particular formula. You don't have to go very far. So this is, like this is part of this Pfaffian theory, but this is just to throw a big word. It's really a simple expansion along matching. And so if you look at the determinant of K along a particular induced cycle, right? So you have S, which is an induced cycle. Okay, so there's no coordinate to it. And so if you look at a particular induced cycle, what you get is that it's the sum of two terms. So the first term here is, so this whole term here, well, actually, it goes all the way here. This whole term is only terms that we can estimate using first and second moments, right? Here is my Kii, we've already known that. And Kij squared, this is something that's actually easy to understand. I don't even have to take the square roots. So all these things, let's agree that we've estimated them with our first and second moment. Then, of course, this only depends on the size of S. And the only thing I don't know is the product of the values of Kij along my particular cycle. So this will be the quantity of interest. So when I compute the determinant of K reduced to an induced cycle, what I'm going to get is something from this I'm going to be able to deduce this product. And if I can do all these things, then I can recover the sign of this product, and in particular, I can recover K up to similarity. Okay, so now I can reduce myself to induced cycles. Okay, and so now, well, that's not true because actually this is not clear that this will give me, this is only the H set of induced cycles, right? So I cannot reduce it just yet, but this formula will be enough to understand this formula only for induced cycles, and we'll see that why in a second. Okay, so this is, I just reproduced this term that we're interested in getting, right? And let's see how well we can estimate this term before we go any further, right? So we're going to use the usual statistical hammer, replace your expectation by averages. And so we're going to estimate the determinant of Ks by, the proportion of realizations that contain the set S. And of course, we're going to estimate that at rate 1 over square root of n. But the problem is that now, the thing that I'm estimating, this term right here is actually can be very small if my alpha is very small. All right, so if all the entries of Kij's are actually of size alpha, which is the worst case in my setup, then what's going to happen is that each of those terms is going to contribute alpha to this product, and so in the end, this product can be as small as something which is alpha to the number of edges in my induced cycle S. And so if I start looking at induced cycles that are gigantic, this thing is going to be very small. So even though I can estimate it at rate 1 over square root of n, then if I want to find out what the sign of this thing is, I'm going to need to have n which is quite large. And in particular, I'm going to need to have n which is exponential in the number of edges of my cycle. Right? So if you think of alpha as being 1/2, this is 2 to the minus 2e to the s. And so that's a problem. Right? If I have a cycle of length which is capital N, this is going to be extremely small. And so the real question you want to ask yourself is, do I really need to consider all those cycles? Are there actually shorter cycles that I should be considering? And it turns out that the answer to this lies in some sort of linear algebraic equations which are referred to as the cycle space. So you can view the cycles of a graph as a linear subspace. And this is an example here. So for example, consider the cycle of length 8 that's in red, okay? And what I want to understand is, can I construct this cycle by adding two smaller cycles? And you've probably guessed that by now. the first thing I can do is consider this cycle right here in blue, and then add this cycle here in green. And when I talk about addition, so here, think about putting a 1 where I have an edge, and putting a 0 where I have no edge, and 1 plus 1 make it equal to 0, right? That's the addition in GF2. And so what it means is that here, since I have 2 colors, this thing will cancel out, and what I've actually built here is just the cycle by adding the blue and the green. So for this particular example, I can actually build the red cycle by adding the blue and the green, and of course, they are half its size. So I don't need to consider the full thing, I actually need to consider only smaller subcycles. Okay, so this idea is certainly not new, and I'm sorry, you're about to see a pretty heavy slide. This is where I use all these definitions. They're not very complicated, but we need just to give you a little bit of what the framework is. So if I have a set of, let's say, simple cycles, I'm not going to go into this, so I'm going to represent my cycles by putting a 1 when there's an edge, so those are in size. So GF2 is the set 01 equipped with addition mod 2, right? And so I take 0, 1 to the m, so those things, so if I have m edges in my original graph, I'm going to put a 1 if it indicates that its presence in a particular cycle, here Cj, and a 0 if it's not in this cycle, all right? And so for each cycle, I'm going to have a vector of size m, where I have a 1 if the edge of this particular, if this edge is in this particular cycle. Okay, and so what I want is to construct a basis of that space. Okay, and so I can list all my cycles, but I want to know if there's actually some sort of a spanning, a subset that can span all those guys. And there's actually something called a cycle basis, and its size is known to be what's called the cyclomatic number of my graph, which is given by the number of edges minus the number of vertices plus the number of connected components. All right, that's a standard result in combinatorics. And what we're going to be interested in, of course, what we want to know is what is the shortest cycle we have to consider. And it turns out that here a basis can always be taken as a basis of induced cycles. And so we're going to try to find the basis that has the shortest, only short elements in it, right? Because the largest element in this basis is the longest cycle we will ever have to consider. So it turns out there's a related notion that arises in combinatorics, which is called the shortest basis. And what they want is the sum of the length of those cycles. They want it to be as short as possible. That's not really what we want. What we want is the maximum to be small. But it turns out that this has a matroid structure, and those two things actually coincide. So whenever you find the shortest basis, you find the one that has the shortest, largest element. And so, so we can just take whatever algorithm there is to compute the shortest basis. And the reference is an algorithm by Horton, which was introduced in the late 80s and recently improved to have a faster running time, and it runs in some pretty decent polynomial. And this algorithm is purely combinatorial optimization, and you just feed it the adjacency matrix of a graph, and it spits out a cycle basis. And there's as many elements as there as the cyclomatic number. All right. So now you could ask, okay, I found the shortest. How long is it? Right? I can always compute that. I know what my graph is. I computed it from my first and second moments. So there will be a longest cycle in this basis. And the largest element, I will call the cycle sparsity of C. And I know that this L is the largest thing I will ever have to consider, because this is essentially the maximum number of KIGs I'm going to be multiplying. And so I'm going to have this alpha to the L that will show up. Okay, so the theorem that goes here is that if K is completely determined up to dissimilarity, K is completely determined by up to similarity by its principal minors of size at most L, right? Principal minors are the determinants of submatrices. So here I have size at most L, if the cycle sparsity of G, if and only if the cycle sparsity of G, the determinantal graph associated to K, is at most L. All right, so this is purely algebraic result, and but this is what we need to understand what the sample complexity is for this problem. So it's telling us just, if you have a graph, so here's an algorithm, right? So let's look at the bottom of this page for a second. I'm going to first estimate my determinantal graph by using first and second moment. Then I'm going to feed it to Horton's algorithm, which will spit out a cycle shortest cycle basis. And then I'm going to estimate the sign in each cycle. So here, of course, I cannot cut through it. I'm going to have to estimate the moments of order Cj, right? So I'm going to have those big things to compute. And then I'm going to have only the signs of the elements of the basis, and I'm going to need to solve for everyone else. And the nice thing about GF2 is that you can actually do Gaussian elimination there, and you can actually solve for everyone, every single cycle. Actually, here we only need to solve for each edge. Okay, and so we're going to apply Gaussian elimination. And if you do this, at the end of the day, you end up with an algorithm that has complexity. Well, here, the Gaussian elimination is a bit of a bottleneck. It costs us m cubed, which m is the number of edges in my determinantal graph, and for which we have the result that I promised in the first place. So just let's go back to it very quickly. The first part here is just to estimate the first and second moments. Pretty standard, halving 1 over epsilon squared, or you can think of it as being the 1 over square root of n rate. And the alpha comes from the square root part. But really what matters is this, say, 2 over alpha. So here L we think is actually, should not be here, but we have 2 over alpha to the power 2L. And this power 2L came from this largest cycle, this longest cycle in the basis that we actually have to consider. And those are actually minimax optimal, and up to this L that we're actually stuck with. Okay, so this is the method of moments, so we can actually solve this problem, and we can also find out what the rate, so we can actually find out what L is for this particular problem, right? So I know what my rate is going to be once I actually estimate my determinantal graph. Okay, so and this L governs the complexity of this problem. Okay, so I have 10 minutes, is that correct? Okay, so here are the takeaways of this first part. So complete characterization, it's adaptive to L because I actually know L, which is nice because I can actually do some confidence intervals and things like this now. And of course, this determinant graph played a key role. So now I'd like to talk a little bit in the 10 minutes that I have left. I'd like to talk about the maximum likelihood. So I have 2 possible ends, and unsurprisingly, I have to go to the fast part. And so this is the fast part of maximum likelihood. Okay? So if you look at the overwhelming majority of the literature, it was written by people interested in optimization, and they said, okay, determinantal point processes are nice. Let's compute the maximum likelihood. It's this not convex thing, but let's do a bunch of heuristics, maybe MCMC, maybe some trying to find some fixed points, maybe trying to do a bunch of different things, okay? And so that's actually where we started, wanting to understand, well, you know, what are the statistical properties of what you're actually trying to optimize. So the maximum likelihood estimator is actually written up there. So when you write it in terms of K, so if you look at the literature, they will write it in terms of L, which is for L ensembles, it's a simple transformation of K, and that's the slides that I skipped before, but you can write everything in terms of K directly. It's a little unpleasant, right? You have the log of the absolute value of a determinant, K minus IS complement. You can imagine that if you're an optimizer, you're going to go for the other formulation that does not have an absolute value in there. It only has like a nice log det in there, and it's little, like, catches your eye when you're an optimizer. And so this is what it looks like. So you have this sum over S, right? All subsets. P hat S is the proportion of times S appeared in your sample. And then you have the log of the absolute value of the determinant. And remember, this absolute value of determinant is what showed up when I did my inclusion-exclusion formula to compute the probability that Y was equal to S. And, you know, we've all taken statistics, or at least, you know, we all have, you know, Van der Waals on our bedside. And we know that what characterizes the rate of convergence is the curvature of the expected log likelihood around its maximum, all right? And that's sometimes called the Fisher information. And, you know, you can write that this is what's going to matter, but it doesn't really tell you how big this Fisher information is, and that's what we're going to try to do. Okay, so the picture is like this. Was obviously not meant for this audience, but essentially here you have curvature around the maximum. Here you have, John, do you have questions about Fisher information?
No, my question is which Van der Waals?
Oh yeah, well, you know, the one.
The yellow one or the green one?
And so anyway, there's one that has statistics in the title and one that does not. Well, actually, now it has 2 to have. All right, so, okay, so now you have this curvature around the maximum, or here you're flat, and here you're actually thinking that if my second order derivative vanishes, I should not have square root of n rate, and this might arise. And the reason it's going to rise is that, remember, we have this exponential number of maxima for this thing that are given by all this similarity. And as soon as I start having certain structure on the K, they collapse with each other. All right? So for example, if K is block diagonal, there's going to be some two a pre and post multiplication by a diagonal matrix that will give me exactly the same thing. And what's going to happen is the fact that those modes start collapsing with each other will actually bring flatness around this maximum, and it will happen as soon as two of them collapse. So yeah, I'm not talking about deep learning, but I just wanted to squeeze in a mode collapsing thing in there. All right, so the thing that's going to be the key, that's what I just mentioned, is this block diagonal matrices. And so a matrix here, K, will be called reducible if it has a block diagonal structure, really, all right, or up to a permutation. Right? I can rearrange rows and columns in such a way that it has a block diagonal structure. And what's going to happen is that this is strictly equivalent to saying that there is a diagonal with plus and minus ones on the diagonal, D, such that K is equal to K dk for some non-trivial D, meaning that the D is not either the identity or negative the identity, for which obviously this will hold. Okay? So now when I have this thing, this will lead that I have modes that collapse, right? And so in this case, you can see that property in your determinantal graph. Since you have two blocks, the sparsity pattern tells you that your graph is split in two connected components. And those components actually correspond to independent sub-DPPs. On each block, you have a DPP, and those two things are actually independent from each other. All right, so there's three ways to view this property. One is this mode collapse, the second one is a graph theoretic one, and the third one is completely probabilistic. You can actually split your DPP. What you observe is actually the union of two independent DPPs. Okay, so what's happening here? Well, it turns out that this is what governs the rate of convergence. If your matrix is irreducible, there's no way to arrange the rows and columns in such a way that it becomes block diagonal, or to say that, I think the simplest one is to say that the determinantal graph is connected. If your determinantal graph is connected, then you get a 1 over square root of n rate, and for the maximum likelihood. And if K star is reducible, it means that it's the union of, or it's a disconnected graph, then you will not get the parametric rate. But the beauty is that your fourth derivative does not vanish, and you still get an n to the 1/4 rate, no matter what K is. Okay, and in the irreducible case, you can even prove asymptotic normality, and so, but we know, we didn't make the same assumptions, though this is pointwise, right? That goes back to Jonas's talk about the difference between pointwise and uniform. So this is pointwise, and we have the square root of n rate. But the real question is going to be, well, what is the asymptotic variance, right? You had the square root of n rate before, and you spent all this time telling us that the constant was what mattered, and here I did not. So what we need to understand is what it looks like, and it's very hard for us to understand what this thing looks like, but what we can show is that when this thing is a very long cycle, then the asymptotic variance is exponential in the length of this cycle. Okay, so, there's no magic going on here. Of course, this was the optimal rate, and the maximum likelihood suffers from the same curse of dimensionality. All right, so this is my last slide. So in this case, of course, the negative expected log likelihood is up to constant is the KL divergence between two DPPs. And you could start asking the question, you said, okay, this thing is non-convex, right? And non-convex is in fashion, so there's a bunch of questions we may ask. And I think, your expertise is required. I don't have a gift for that, but you can imagine one. And so the question is, what do critical points look like, right? We know there's already an exponential number of them if my DPP is irreducible. We can show, actually, and that's not actually easy, we need to use some pretty deep properties such as conditional negative association for DPPs. We can actually show that you can find already an exponential number of critical points by just looking at all the sub-DPPs. All right, so if I give you a DPP, even if it's connected, you take a sub-DPP, this sub-DPP will give you a critical point. Gradient will vanish. All right, that's a lot of them on top of all the global minima. And we all know that those guys are all saddle points. That's nice, right? And they're not local minima. And the thing we don't know how to answer is, are there any other critical points. Because if there's no other critical points, since we have the saddle point, this gives us hope that maybe, you know, gradient descent or perturbed gradient descent, say Langevin type things can actually get you to the minimum. What I think is actually amusing about this point is my colleague Savitra has a result on this, and that was a good inspiration for me. And he's actually using an algorithm that's looking for fixed points. And I think this tells you should certainly not do this because there's just too many fixed points. You should not use a fixed point algorithm. You should just perturb and try to escape those saddle points. So here our results is very partial. We only know that there's one escape, at least one escape direction for those saddle points. It would be nice to show that there's actually big ones. There's a bunch of other statistical questions we didn't answer. For example, what is the performance of the maximum likelihood estimator constrained to having the right sparsity pattern in the case when you have a reducible one, right? So if you're reducible, you can actually see the blocks. And you could say, well, let me estimate the maximum likelihood estimator on one block, maximum likelihood estimator on the other block, and then put them together. And presumably this should have square root of n rate. Of course, we didn't do minimax. So for the first example, what happens if we allow, like, what is this rate? If we don't want 1 over root n rates, clearly if I let alpha go to 0, I will have rates that are certainly suffering from the curse of dimensionality, something like 1 over n to the 1 over L. And so how do you characterize those things? It's a little bit of a moving target. It's a little difficult. And of course, you know, if you're more interested in methods and setups, Francis has a nice work with his former student, Christophe Dupuis, and you know, you can put some structural assumptions on K or some things related to K. For example, you can assume that K has low rank or is, you know, has a sparse representation in an appropriate basis in general. Yeah.
So if it is low rank, the determinant is 0.
If it is, yeah, so near low rank. And actually, when I say on K,
Additive T plus low rank. Okay. Not that stupid.
And but you can write that paper with just K equal is low rank. This is yours. And so you can put and you can write them in different bases, and there's many setups that you can actually consider putting structure. And you know, if you look at Taskar's about Kulas and Taskar's book, there's actually some sort of parametric modeling for K itself. All right, so with that, I will you go to coffee. I know I need one. Thank you very much.
So for graphical models, the sparsity pattern has a true interpretation of like conditional independencies. In your case, what does a zero mean in your determinantal graph?
For a particular edge, well, for a particular edge, it's telling you that those two, right? So there's actually a nice formula, and I actually totally forgot to. So if you look at the first, look at the probability that jk is included in y. This is kjj times kkk, which is the probability that j is included and that k is included. If they were independent, this would actually just be the probability that they're included together when they're independent, right? And this kjk, this is why this thing is actually promoting diversity, is saying, well, if both are included, I'm going to remove some non-negative number. So when you have 0, it's saying that they're independent, and when you have non-zero, it's saying they're not independent. Now, of course, there's some much more complicated things that are going on at a higher level, but at the pairwise level, this is what's happening.
So what I'm getting at is like sparsity a good assumption for K? Does it relate to anything like in terms of modeling? Is it like a good class of models for applications?
Well, not for interpretation, right? I mean, you know, it is a structural assumption, and I don't think it's a bad one. You know, for example, okay, think about the block diagonal case. If you're thinking that you have block diagonal, why would, I mean, it's sort of reasonable to assume that in the, I don't know, in the example of electronics, you would have subsets of electronics, maybe the bags, maybe the screens, or all these things that tend to be independent of each other.
It's a bit similar to the zero is the covariance matrix is different from zero in the inverse. So
yeah, but I remember having a discussion maybe 10 years ago with Peter, and I was like, I just couldn't understand, why do we actually, like, why would the modeling arising from the inverse covariance matrix, why would it be more, the clustering that you get from that, why would it be more attractive to the one arising from the covariance matrix itself? We have a nicer story to tell, but I don't know if those conditional independent things, you know, how they arise. Usually there's a bit of selection bias in the pictures that you see in papers.
No, for instance, okay, if you have structural equation modeling, then that is a natural way of modeling that gives independence in the
Yeah.
in the inverse covariance, right?
Yeah, but then you deferred your modeling to structural equation
No, but
models.
it's a natural way to think, right? This causes this causes that. And
Yeah, but then there's all these confounding factors that you don't know.
This is a really naive question. I'm just not. I haven't seen the cyclosparsity stuff. What's the cyclosparsity of the complete graph?
Like it's 3.
It's 3.
That's the smallest cycle, right?
It's just, okay.
But if
It's
you have
just, it's just triangles everywhere.
Yeah.
So if you had something where everything was bigger than alpha, then your problem is actually quite.
Yeah, so actually, we deferred this question until about 2 weeks before we were planning to originally submit this paper. We're like, yeah, we need to only estimate moments of order 3, it's going to be trivial. And then actually the most interesting part of the paper arose because actually there's a lot of, there's work in algebraic statistics, right? So there's Lukhodin, for example, and all these people consider the dense case, and they show that the Grobner basis has degree 3 and things like this, but everything that's dense is really like a low degree polynomials that show up. But as soon as you start being sparse, then you start running into those issues.
Sparsity actually makes everything harder.
Yeah, sparsity makes everything harder, so that's also a good reason why I would want to do this.
I think in the sparse case, the estimates are not sparse, right? So when you use the
In the sparse case, the estimates are not sparse.
hat,
No, the estimates are sparse, right? The sparsity pattern I recover with the first 2, when I do k-hat, the first 2 moments, right? So when I actually, it's on this slide, when I look at this guy here, this thing, I will actually figure out, I see what you're saying. Yeah, I can, okay. So the determinantal graph is thresholded at, say, alpha over 2, or, I don't know, 1 over log n if you want, anywhere you want, that's away from 0. Yes, you're right. So this is not sparse the way I wrote it, absolutely. It should be, maybe I should put a sub-alpha.
I mean, related to that point, I mean, you mentioned if the cycle is long, right, you have the product of small values, and it's a problem because you cannot estimate that well. But I mean, if you would kind of truncate that or so instead of your cycle, basically the shorter cycle, would that be an alternative approach to get around this problem?
If I truncated this, you're saying if this value is too small, I would put it to 0? Yeah, I think, so.
If that product is actually small, does it matter a lot in your final estimate?
Well, first of all, yes, I have an L infinity. No, okay, so yeah, no. If it's smaller than the rate that if it's smaller than epsilon, it won't matter. But the thing is that there's lots of cycles colliding with each other, right? So if I start putting a bunch of cycles together, then they can have a significant impact on the. Okay, if all my values are small, sure, I can estimate it by 0. But there's definitely a regime where alpha is not that small, and alpha can be certainly much larger than epsilon, and still, if alpha is 1/2, it's still much larger than epsilon typically, or the rate at which I want to estimate this, and it is a problem, right? Any alpha less than 1, you shouldn't think of alpha as going to 0. Think of alpha as being, 1/2. And in this case, I don't know, but I don't like to threshold at 1/2 and call it 0 if that's the case.
Maybe we can continue again and